Hi everyone, Charlie Sink here. I've been working on this little project. It's an electric locomotive for my backyard railroad. Railroad has 7.5-inch gauge track. This runs on 2 electric moped motors and a couple of moped batteries. Here's the CAD of what it'll look like when it's finally done. And I needed to bend up some grab irons for the locomotive cab sides. So I looked around for commercial rod benders. I didn't really like anything I saw, so I decided to build my own. So this video is the process of CNCing the various parts. And the video turned out way longer than I originally planned. So if you just want to see the rod bender bending some rod, skip to the end of the video. But if you want to see how the parts are CNC'd and turned on the lathe and how the tool paths are set up, stick around. Welcome to another edition of the Weevil Genius. So here are the materials. A 1/2 inch by 3 inch mild steel piece for the base, a scrap of mild steel for the clamp block, a piece of 1/2 inch by 5/8 inch mild steel for the bending arm, and some stainless rod for my scrap box, probably 303, and some 1-inch wood dowel. To machine the parts, a Tormach PCNC 1100 for doing the CNCing, an old Series 1 Bridgeport, and the Grizzly 14x40 gearhead engine lathe. For doing the milling, I had a nice brand new 4-flute high-speed steel 1/2 inch end mill, but as it turned out, it was about a 1/4 thou too large to fit in the holder. Go figure. Several interesting options for pushing it into the holder instantly came to mind. In the end though, I chose probably the worst idea I had. This is a tortured 1/2 inch carbide end mill I used on some previous learning curves. The only thing it really had going for it was that it actually fit the TTS holder. Okay, moving on. So let's get started. First part is the base block. It has notch sides so it can be easily clamped in a bench vise. It also has a hole for the bending pin and a pocket for the clamp bolt and nut. All the tool paths were set up in Fusion 360. First off was just truing up the ends of the block. Light, easy, very conservative cuts. These were set up in Fusion 360 as contour operations. The second operation was to cut the side notches so the base block could be clamped in a bench vise, which I set up incorrectly. The cut ended up with a 3mm step over at 7mm deep, which I would have caught if I'd run the simulation. Here's the simulation. Way too much for that dull end mill. And here we go. The camera vibration is coming from the mill through the shop's concrete slab. I could also feel the cutting vibration through my shoes. Not good. I didn't think to get a close-up at the chips, but you can see that they have inconsistent heating, with some that got pretty hot and a lot that didn't. The chips looked like they'd been ripped from the stock. Must have been a dull end mill. And when the cut finished, I noticed that the TTS holder had about a 1/2 mil of pullout, and the stock had been pulled out of the vise by the same amount. The rest of the cuts on this part were done with 1mm step over. Then I threw the end mill out. Again. The next stop was milling the pocket for the clamp nut and drilling a pilot hole for the bending pin. Holes were drilled in the pocket area to help with chip evacuation. Here's how the setup looks in Fusion. And here's the simulation. On to the bending arm. Contour and chamfering operations were used on both ends and then chamfer over the sides. Holes were drilled on the old Bridgeport. And by the way, in this video I really didn't want to go deep into how to work CAM and Fusion 360. If you're interested in learning Fusion 360 and anything CNC, check out John Saunders' extensive library of video on the subject at NYCNC. I'm a SolidWorks guy, but he's pretty much the reason I got into Fusion 360 and bought a Tormach PCNC 1100. This is a link to one of his videos on how to set up tool paths for chamfering. He knows a ton about this stuff. Check out his videos, it'll be worth your time. This is the chamfer bit I used for chamfering all the parts on the project. It's a 1/4 inch solid carbide 4-flute chamfer bit. Okay, moving on. Okay, moving on. The clamp block machined pretty much the same way as everything else. I somehow managed not to get video of how the trough was CNC'd. So here are the tool paths in 360. And here's the simulation. The hole and the backside milling were done manually on the Bridgeport. To get a nice finish on all the CNC parts, I used 320 grit wet and dry sandpaper. Several minutes of sliding the parts back and forth on the sandpaper that was on the granite surface plate did the job. Keeping the sandpaper wet helped a lot in moving the used sanding grit and steel particles out away from the part. Next up was the clamp bolt pivot block. It allows the clamp bolt to stay vertical while the clamp block pivots at different angles while using different diameter rod. Searching through my scrap drawer, I found a nice bit of 3/4 inch diameter mild steel, left over from something. The part was in this thing somewhere. I just needed to remove some metal to reveal the masterpiece that this would soon become, or something. Next up was the clamp nut. It was so simple I didn't bother setting up tool paths with the Fusion 360. I did all the milling and drilling on the Bridgeport and then tapped at 1/4 20. Okay, moving on. This is the clamp bolt. It was machined from 1/2-inch stainless rod, probably 303 judging by how well it machined. All operations were done on the lathe, and the hole was drilled manually on the Bridgeport. Thread is 1/4-20. I really need to get one of those tailstock die holders, but until then, the method you'll see in a minute seems to work well enough for now. The wood handle was turned and faced on the lathe. I had some material left over. After pondering what to do with it for a minute, I found a good use for it. That of course involved some CNCing. More on that in a minute. The handle retaining bolt, bending pin, handle pin, and roller pin were turned and faced on the lathe. If I was a real machinist, you would probably be expecting me to press all these parts together. Since I'm not a machinist, I'll save myself a lot of trouble and just use Threadlock to hold the various bits together. Out of curiosity, I was going to calculate the force needed to push the bending arm pin out of the base block. Consulting the back of the package, I discovered the shear strength for high-strength Permatex is NA. Whiskey Tango Foxtrot? Utilizing logic and deductive reasoning, I concluded that the shear strength must be somewhere between 0 and infinity, based on the available information. Since I don't think the engineers at Permatex can make an infinitely strong Threadlock, and marketing is probably smart enough not to sell Threadlock with 0 strength, I concluded that the strength is probably just really strong. I like building stuff that's really strong, so I'll stick with that. The Threadlock joints are really strong. I also read someplace that not allowing the tip of the bottle to come in contact with the metal prevents clogging. Since I started adhering to that rule, I've never had a bottle clog. Okay, on to assembly. I'm actually really happy with how this turned out. I love the look of the steel and the feel of the beveled edges. Thanks for watching. I hope you liked the video. See you next time.